In this video, we're going to talk about optimization of quadratic forms. This is a more advanced topic that probably is more suitable for a second course in linear algebra than a first course, but I wanted to talk about it because it leads to a discussion of something called principal component analysis in statistics. And I want to explain in the next few videos how this stuff we're talking about when it comes to the spectral theorem and quadratic forms and eigenvalues and eigenvectors, how those theoretical facts apply and those concepts apply to a statistics technique that happens when you're looking at data. And to understand how all that works, let's review some facts about quadratic forms. So we've seen that when you have a quadratic form, let's review what a quadratic form is. So a quadratic form in n variables is a function or an expression of n variables x1 through xn, which is given by taking the vector x1 through xn as a row and then multiplying it by a symmetric matrix A times this column vector x1 through xn. So where A is a symmetric matrix. And just in case you don't remember what symmetric means, it means that its transpose is equal to itself. Okay. And we've seen that we can get a better idea, we can get a better understanding of quadratic forms by using the spectral theorem. So let's just remind ourselves what the spectral theorem says. It says that any symmetric matrix, and we're talking about matrices with real entries, has the form Q lambda Q transpose, or Q inverse. It's the same because Q is an orthogonal matrix. There's an orthogonal matrix Q and a diagonal matrix lambda such that A is equal to Q lambda Q transpose. And how does that help? Well, our quadratic form x1 for xn is equal to x1 for xn times A times x1 through xn. And the point is that if you take Q transpose times this column vector x1 through xn, if you define new variables u1 through un by u1 through un is equal to this Q transpose times x1 to xn, then what happens is that you can write f, this quadratic form, in terms of u1 through un. And what happens is that this part here is equal to the row vector u1 through un. And so what you get is the row vector u1 through un times lambda times the column vector u1 to un. By the way, how do we know that this part, the row vector x1 through xn times q is equal to the row vector u1 through un? What happens is you can take the transpose. You take this equation and transpose both sides, and what you're going to get is, so maybe I'll just do a little cloud, okay, a little thing on the side. If you do the transpose of q transpose x1 through xn as a column, by the fact that when you have, okay, I'm running out of space, but there's this fact that if you do A times B and transpose that, that's the same as B transpose A transpose. So if you apply that in this scenario, you're going to get the transpose of the column vector x1 to xn, that's the row vector x1 to xn, and then times A transpose. Well, A is Q transpose, and if you do Q transpose transpose, that's just Q. So that's how I get that. Anyway, so that's how we get that. And we get this. And now let's say that lambda, this matrix lambda, that's a diagonal matrix where the diagonal matrix entries are the eigenvalues. Remember that the UIs are unit length eigenvectors of A, and the matrix lambda 1 through lambda n consists of the eigenvalues corresponding to those UIs, those vectors UI. Yeah, lambda 1 through lambda n. Well, in this case, just to clarify, these UIs are variables, but these eigenvalues correspond to the eigenvectors, which are the columns of Q. Okay, so those would be the vectors U1 through UN. Now, it's typical when you use the spectral theorem and write A as Q lambda Q inverse, you can always rearrange things. You can rearrange the lambda i's so that lambda 1 is greater than or equal to lambda 2 is greater than or equal to lambda n. In other words, you arrange them from greatest to least. You don't have to, but it's possible to do that. Okay. And we're going to do that. When you switch the order in which you write the lambda i's, then you end up switching the order in which you write the q, right? You just rearrange those vectors. Okay, so what this ends up being when you write all this out is just going to be lambda 1 times u1 squared plus lambda 2 u2 squared plus dot 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 plus lambda n un squared. And so what happens, what we've done is we've started out with this complicated quadratic form, right? Just a general quadratic form, and after using the spectral theorem, we see that if you define new variables u1 through un, then the quadratic form has a very simple form. Okay, let's take a look at an example just to review how this works. So let's say that you have the quadratic form f of x1, x2 equals 3x1 squared plus 4x1, x2 plus 3x2 squared. Okay, this is a quadratic form in two variables. And let's try writing the quadratic form using two new variables without these so-called cross terms, right? You see that here, we don't have anything like u1 times u2 or u3 times u4 or anything like that. Each of the variables are separate. And that's what we're going to do with this one. Right now, the variables are not separate because you have this x1, x2. And so the question is to rewrite this quadratic form with no cross terms. Well, we just went over how to do that. First, we need to find the matrix of this quadratic form, and then use the spectral theorem. So first of all, we know that f of x1, x2 is equal to x1, x2 times some symmetric matrix times x1, x2. What matrix is going to go there? Okay, why don't you take a minute and see if you can figure out this matrix. All right, let's go over the answer. It's this matrix. Right? You take these numbers that are being multiplied by x1 and x2 squared, you make them these diagonal entries, and then you take half of the number being multiplied by x1, x2, and those go here. And then if you multiply all this out, you're going to get this. Okay. So that's our matrix A. It's a symmetric matrix, as we see. Its transpose is equal to itself. And we need to find the lambda and the q, and that's done by finding the eigenvalues and eigenvectors of this matrix. So first, let's find the eigenvalues. This is a 2 by 2 matrix, and so we know the simple formula for the characteristic polynomial. It's lambda squared minus the trace, minus the sum of the diagonal entries. That's 6 lambda, and then plus the determinant. And the determinant of this is 9 minus 4 is 5. So you get plus 5. That's the characteristic polynomial of A. And to find the eigenvalues, we set that equal to 0, and we solve for lambda. And at this point, you can use the quadratic formula, or you can factor. In this case, it's pretty easy to factor. You get this. And so you get lambda is 1 and lambda is 5. And remember, we're arranging things so that the eigenvalues come from greatest to least. So let's set lambda 1 to be 5, since that's more than 1. So then a minus 5i, we're finding the eigenvectors. We do a minus lambda I. We get this matrix. And we need to find one vector in the null space of this matrix, and that's going to be, remember, for this 2 by 2 matrix, you can just look at the first row, and then since it's a 2 by 2 matrix, you can just swap the components and then stick in a negative sign. So you can use, well, you can use 2, 2, but it's even easier to just use 1, 1. Actually, it doesn't really matter because we're going to have to find a unit length vector. We're going to normalize this, so the length of this vector is root 2. So we need to divide by root 2. Remember, in the matrix Q, the eigenvectors have unit length, so we need to do this normalization step. So that's lambda 1, and now lambda 2 is 1. We just do the same thing. A minus I is this matrix. Okay, we get that x2 is going to be, say, negative 1, 1. And when you find a unit length vector, its length is root 2 again, negative 1 over root 2, 1 over root 2. You can also use 1, negative 1 instead of negative 1, 1. Okay, so our matrix, our so-called diagonalization of A, we're writing A in the form Q, lambda Q inverse. Our Q is going to have columns U1 and U2. That's Q, and then lambda is 5, 1, and then Q inverse is just the transpose of Q. So we can just write it easily. Yeah. Okay, so this is our Q, that's lambda, that's Q inverse, or Q transpose. And so how can we write this quadratic form in terms of our new variables, u1 and u2. It's going to be given by this, by this matrix, right? So if we define u1 and u2 by this q inverse times x1, x2. Okay, I'm not going to write all this out, but u1 is just going to be 1 over root 2 x1 plus 1 over root 2 x2. u2 is going to be negative 1 over root 2 x1 plus 1 over root 2 x2, right? Then our quadratic form, f of x1, x2, is equal to 5u1 squared plus 1 u2 squared. Okay. Okay, so this is going to be a bowl shape, right? The 0.00 is going to be a minimum. By the way, this u1 and u2, here I'm using u1 and u2 as variables, right? It's not the same as these vectors u1 and u2. Okay, let's think about how else we can use this fact. Now that we've written our quadratic form in a simpler form in terms of u1 and u2, how can we use this fact? Well, for various reasons, we're going to have to consider this question. First of all, this function, if you think of this as a function of two variables, there's no maximum, right? Because you can just make u1 and u2 as big as you want, and then there's no preventing this from being as large as you want. I mean, the values of this will be arbitrarily large. However, what you can do is, what happens if you require the vector u1, u2 to be a unit vector? So the question we have is, what is the max min value of f of x1, x2 when x1, x2 is required to be a unit vector? Well, we can actually use this expression for the quadratic form, because notice that when x1, x2 is a unit vector, so is the vector u1, u2. Okay, that's a general fact that if you take an orthogonal matrix, Q inverse is an orthogonal matrix. Okay, if your input vector x1, x2 has unit length, so does u1, u2. So u1, u2 is also a unit vector. And so what we have to do is so u1 squared plus u2 squared is equal to 1. So the question is, what are the biggest and smallest values of 5u1 squared plus u2 squared, given that u1 squared plus u2 squared equals 1? Well, let's look at 5u1 squared plus u2 squared. First of all, this is certainly less than or equal to 5u1 squared plus 5u2 squared. Right? Because u2 squared is less than or equal to 5 times u2 squared. u2 squared is a non-negative number. But what can you do with this 5u1 squared plus 5u2 squared? You can factor out the 5. And that's 5 times the quantity u1 squared plus u2 squared. And when u1, u2 is a unit vector, what's u1 squared plus u2 squared? It's equal to 1, right? So This is 5 times 1, which is 5. So what that means is that 5u1 squared plus u2 squared is always less than or equal to 5. No matter what u1, u2 is, as long as it's a unit vector. But is it possible for 5u1 squared plus u2 squared to be 5? Can you come up with a unit vector u1 and u2 that will make that equal to 5? Well, yes, the value 5 is obtained. The value 5 is attained when u1 is 1 and u2 is 0. So what that means is your function achieves the value 5 and it's never bigger than 5, so the maximum value of f of x1, x2 is 5, and this is attained when, what's x1, x2 equal to? Well, it's when u1 is 1 and u2 is 0. And when u1 is 1 and u2 is 0, what's x1, x2? It's going to be the first column of Q. Okay, because, let me just explain that real quick. This matrix is Q inverse. So u1, u2, so x1, x2 is going to be Q times u1, u2. Okay. Right, just by multiplying on the left by Q. And so if u1 is 1 and u2 is 0, then x1, x2 is just going to be the first column of Q. So Q times 1, 0 is the first column of Q. And that's this eigenvector u1. So it's when x1, x2 is 1 over root 2, 1 over root 2. And the same thing can be said for the minimum value. The minimum value, so for the minimum value, 5u1 squared plus u2 squared is going to be greater than or equal to u1 squared plus u2 squared, and that's 1. But the value 1 is obtained, and the value 1 is attained when u1, u2 is equal to 0, 1. And that's the same, i.e., when x1, x2 is equal to, well, it's Q times 0, 1. That's the second column of Q. That's negative 1 over root 2, 1 over root 2. So now we see a new way of thinking about these eigenvalues and eigenvectors, right? Notice that 5 and 1, these were the eigenvalues. So the max value was 5, the min value is 1. These were the eigenvalues of A. And these, okay, the x1, x2, in which these max and min values were obtained, okay, these were the eigenvectors that we found, the unit eigenvectors of A. So this leads us to a new way of thinking about eigenvalues and eigenvectors, and we're going to explore this more in the next video. Okay, thanks.